Welcome to the fourth day of GAN program on zeros of L functions. Yesterday we stopped at a theorem where which was necessary for proving the prime number theorem via Newman's method. Okay, and this was okay. Let's do just a recall of what we have done till now about the prime number theorem. And this is pi x is of the order x by log x is of the order x, which is equivalent to show that xi x is of the order x as well, and then that is equivalent to show that the integral from 1 to infinity xi x minus x by x square dx converges. Okay, and now in order to show this, we would prove this theorem that if g s is a function that is analytic in real part of s greater than or equal to 1, such that gs is equal to this integral from 1 to infinity fx by x to the power 1 plus s dx for real part of s greater than 1 for some function fx which is big O of x, then g of 1 is given by the integral from 1 to infinity fx by x square dx. Okay. In particular, we would put this fx as xi x minus x. Okay. We already know that xi x is big O of x, so xi x minus x satisfies the condition on fx. Okay.
Sir,
Yes.
it is both equivalent or one side?
Which one? Ah, right. Yeah. Sorry. Thanks a lot. Yeah, we have shown that if this converges, then that will imply that xi x is of the order x. So now we interpret this. We just made some substitutions, like we have put s equal to 1 plus z, x equal to e power t, and just define zz equal to g of s and capital F t as capital F x as fx by x. Then this theorem we restate it as theorem dash, say, and that is if gz is a function of z which is analytic in the region real part of z greater than or equal to 0, or a function that is in real part of z greater than or equal to 0, then and also there exists a function capital F okay, I use this part of the board. Okay. gz is a function that is analytic in real part of z greater than or equal to 0, then and there exists a bounded function if such that, so gz is, well, it should be the integral from, because we are replacing x with e power t, this will be the integral from 0 to infinity f z by e t z dz, sorry, dt, excuse me. Okay. For all z with real part of z greater than 0. Okay. Then g of 0 is equal to the integral from 0 to infinity just fz, because t is equal to 0. So this one is just 1. Okay. Fz. Wait a minute.
So it is f e to the power t.
If
Capital F e to the power t.
right, yeah, that was the thing. Yeah. So thanks a lot. Yeah, that was the thing, because it was fx, right? Thanks. Thank you. So f e power t dt. Okay. So we are going to show this, and in order to show this, we defined an auxiliary function, that is gt, which is a truncation of g from the, instead of this integral from 0 to infinity, we are taking the integral from 0 to t. Okay. Right? So integral from, we defined gt z as the integral from 0 to t of the same thing, f of et by e power tz dt. Okay. I note that since this is a bounded function, this function is going to be analytic everywhere. Okay. Now we have to show, so this one now boils down to show that g0 is a limit of gt0 as t goes to infinity. So suffices to show that g0 is a limit of t going to 0, t going to infinity, excuse me, gt 0. Okay. And we want to show this via contour integration over some nice dome, no, some nice contour. Okay. So this is just limit of t going to infinity g0 minus gt 0 to be equal to 0. That's what we want to show. Okay. So now note that g0 minus gt0, this is, okay, by Cauchy's ratio theorem, we get that if we define some, if the function that we are writing on the right hand side over some contour over on the right hand side, if it has a simple pole at 0 and is analytic on the everywhere on the contour, then we will get here that this is, yeah, so the contour at first we don't know, before we describe the shape of the contour, all we require is that this should go in some region around this, and where in this region, there will be a simple pole only at, and the problem will be only at the origin. Okay, so this one we are integrating over some contour C, and this is gz minus gtz, and we said that we need some kernel function here, that is e power zt 1 plus z square by r square by z. Okay, this is giving rise to the residue. Now what we, okay, now we define the contour precisely, on what contour we are going to do this integration, and then we will handle this part by part on different parts of the contour. Okay. So this one was a contour that we are considering. Take the unit circle and so two other chalks. Is it visible? Green on green? Okay. And also we saw that since G0, GT is analytic everywhere, right? And G0, I mean GZ is given to be analytic in this region, real part of Z greater than or equal to 0. So every point has some neighborhood in which the function is analytic, right? And since it's a compact region, you can take a finite subcover and take the minimum radius of the open ball around the points. So you can take actually a cover with open balls around each of the point and take the minimum radius of the such balls then in that compact subcover. Okay, so that gives you some radius delta where you can extend this. Okay, so you are extending the circle and you are taking this region, this closed region. So this part is open, the green part is open, and this first part is closed, say. So here we are, I mean, we are extending the, because we will treat this, I mean, treat the integral on this part and treat the integral on this part separately. Okay. Now for this part, the green part, okay, that is where the real part of z is greater than 0. Let's consider this first. Sorry. Yes. Yes. So you can. Have I used capital? Ah, right. Yeah. Sorry. So this is the radius of the circle, and t is just the point of truncation of this. Okay. So there are two things which we are going to vary later in the proof. That is this capital R and t, and this distance is just delta, some delta. Okay. So yeah, or yeah. So you can actually mark this point. We'll call this just minus delta 0. Okay. This point. All right. So now we are going to handle this green part. So real part of let's write it down here. That is real part of z greater than 0. Okay. And there, what happens? The integral over the green part, over the, I mean, the part of the contour which is here. So we can actually call this part, say, the positive side of the contour. So C plus maybe, and this one the negative side, C minus. Okay. So the integral of the thing on C plus gz minus gtz est 1 plus z square by r square dz by z. We first consider this one. Okay. All right. Now look at this one. Okay, gz minus gtz. What is that? This is the integral from t to infinity, right? T to infinity of f et by e tz dt, right? Now note that f is bounded, right? So suppose it is bounded by some constant. Okay. So suppose if et is bounded by some constant c. Okay, we are using there c and c plus, so maybe we use some other notation here. Maybe bounded by b. Okay. And then this one is bounded by b t to infinity 1 by, sorry, okay, wait a minute. So if we take the I need some more space also to write this one. Can I clear up this part of the board? Thank you. Okay. So this one is bounded by the integral from t to infinity of f et by power tz dt, which is equal to, well, which is also bounded by, because this is bounded by b, so this is bounded by b times, yes, which one? Z. Z is a complex valued number, yes, of course. In which one? Ah, right, thank you very much. Yes, I am considering the mod. Thanks a lot. Yeah, thank you, Shujit. So this one is bounded by b times t to infinity dt by, well, then what we get in the denominator, it is etz, and that is, we saw this earlier, right? The real part of this. Okay. Yeah. Okay. So this is just b times, and what's that? Can we do this integral? Yes. Minus real part of, okay, wait a minute, minus real part of z times capital T, right, by real part of z. Okay. Because we are considering z to be on the positive side. Okay. So this part is bounded by such an expression. Okay. Now look at the, well, we have not yet considered what happens after you multiply this, but that would be easy. Okay. So if you take the absolute value of this on this part of the contour, what happens? Okay, consider that e power zt 1 plus z square by r square. So this one is this one on this line, okay, on the green part. This is what happens to e power zt. Yes, but it is e power real part of z times t. Okay, exactly this one, but without this negative sign. Okay. E power real part of z times t. Okay, the first thing. Okay, and now how this times this, you multiply that inside. Okay, you get here z by r. Okay, and here it is just 1 by z, right? So you have here 1 by z plus, no, not z by r, but z by r squared. Okay, we'll take one r out. Okay, so which one? R, right, sure. Yeah, so thanks a lot. So this is 1 by z plus z by r squared, right? Okay, and then if you take one r out, what will happen? E power real part of z times t by r times r by z plus z by r, right? Okay, all right, I'll clear up some part and then we proceed with this. So if your point z is on the circle of radius r, then can you say what is z bar equal to? It's on the circle of radius r, root r square, right? It's r square. So that means z bar by r is equal to r by z, right, on the circle. Okay, so you can replace this r by z with z bar by r when you are on this green line. Okay, so this becomes then e power real part of z times t by r, and here you have z bar by r plus z by r. Okay, what is that? Right, so this is 2 into real part of z by r. Well, we can also put, okay, but real part of z is positive, right? So we don't need the absolute value anymore here. Real part of z by r times this thing what was outside, so e power real part of z times t by r, another r. Okay, so it's r squared and e power real part of z times t. Okay, all right, so that is the absolute value from this one. Okay, and when you multiply this and this, what happens? Because we are considering this entire integral on this part, on the part c plus. Okay, so you multiply this, you see that e power minus real part of zt, this gets cancelled with this one. Here there was a real part of z which gets cancelled with this one, and there remains only 2 by r square here and b here. So the product of these two things. Okay, that implies that this integral on the green part is bounded by 2b by r squared. Okay, exactly, yeah. Choice of this kernel was such that this cancels, right? Okay, so on the green part, or on C plus C plus, we have written just. We have that the integral 1 by 2 pi I integral from, well, just this integral, right? We don't have to even consider this one at the moment. So this on C plus G Z minus G T Z times E Z T 1 plus Z squared by R squared dz by z. This integral remains bounded by 2b by R squared, right? Yes. Instead of, again, right, integration of dz. Okay, we have just divided this. Okay, let's write it down again. So this part was, this is less than equal to integral of C plus, okay, GTZ times EZT 1 plus Z squared by R squared, uh, 1 by Z. Okay, wait a minute. So we handled this this part together. I mean separately, this kernel and this one, right? Okay, and then we saw that this integral is bounded, and this is bounded by some constant which is cancelling with this part, right? Now, okay, you are saying that what happens? I mean, with dz, but aren't we multiplying it already? I mean, didn't we consider this integral? This integral we have already considered, right? And then we have shown that this remains bounded by this thing. Okay, so wait a minute. Yeah, yeah, tell me again that. Oh, we can do that again. Yeah,
Integration C times HZ.
yes,
We take the bound of HZ.
yes,
Integration of DZ.
right,
Taking the bound of not HZ.
okay. And so, yes, of course, I mean at most there will be an extra r which cancels with this r squared, right? Because this is a bounded region, right? So, and the length of this is just pi r, right? So there will be some constant times an extra r. What? Which inequality? You are integrating over a contour, right? And then your z is moving over this contour. So at most it can contribute the length of the contour, right? So Ria was saying that there will be an extra factor of dz, okay, which can at most contribute over this contour of length c plus the length pi r, right? Can it contribute anything more? Because you are taking the absolute value. I mean the length of that contour integration over a path. What does it mean? Okay. Yes. Okay. Just tell them. Yes. Okay. So this one is then bounded by some constant, well, maybe b dash then by r, right? And then we have this on the left hand side. Okay, this c minus should also be considered, right? And here, well, here we first consider just this one, GTZ. Okay, so now on the yellow part. Okay, note that here GTZ is equal to how was it defined? F e power t by sorry, it was e power tz. Thank you. Yes, e power tz and dt and the integral from 0 to t, right? So over this part again, this remains bounded by some constant b, say. So that means this one. Oh, we also should consider this kernel multiplied with it, right? Is also the same. It's analytic everywhere, right? So instead of taking the contour over c minus, we would have also taken it over this path, and that would have not changed the value of the integral. Okay, there is no pole or anything in the in between. Okay. So that means that this is okay. This is equal to, call this part some c minus tilde. Okay. So this is equal to c minus tilde, that is the changed contour, okay, of GTZ e zt 1 plus z squared by r squared dz by z. Okay. And now on this part again, we know that the value of this we just calculated here, right? This is e power real part of zt by r, and this one everything is fine because we are again on this part of the circle, right? So this r by z we can again replace by z by r, and that would give you 2 times real part of z by r squared. Okay. So this is giving you then what? Okay, part contribution from this is coming out to be this one. Only here would be a mod because now real part of z is negative. Okay, and I mean mod means the absolute value of real part of z, and then GTZ. Now note that GTZ was just this integral from 0 to t of f e t by e power tz dt, right? And this remains bounded. So if you take this, then this is less than or equal to b times, again you are just left with doing the integration from 0 to t of e power dt e power tz, okay, 1 by e power tz, and that gives again the factor what, e to the power minus t real part of z, and below that is absolute. Okay. real part of z, right? Okay. Which one? Minus of 1 by minus of 1 by yes, right. Yes, some constant may still remain there. Okay, so plus some constant. All right, and oh, wait a minute. Does it? Let's check. So at uh, wait, this is p times e power minus t real part of z. No, it should be exactly this one. What? F of 1. Well, right, at f of 1 it is okay. There should be a value at f of 1 and that corresponds to the that if we set it to be 0, then this vanishes, right? Yeah, but can we set it to 0? Let's check. um, yeah, actually our f of well, f of 1 should be like xi at 1, right? And x is so xi x minus x at 1 at x equal to 1, right? And we can of course set it to be 1. um, can't we? It's a what is the value of xi? Okay, xi at 1, how can we? It's not a multiplicative function, of course. It's it's I mean, if we take a multiplicative function, it's natural to start with 1. But wait a minute. So let's maybe work with that constant here and see what happens. Okay. Yes, xi of 1 should be 0, but we are working with xi of 1 minus xi of x minus x, right? So xi of 1 is 0, that's fine, but we are now working with xi of x minus x. Okay, capital F. Well, capital F was fx equal to fx by x. Okay, let's see. So b is a bound for this, and then we are basically putting the limiting values of this in this, and therefore this should be just e power 1 by okay, right, it would be 1 by real part of z, right? Okay, yeah. So instead of this one will have this plus 1 there, right? And we'll see that whether that's making a problem. Okay, minus 1, right? Yeah, yes, of course, because this may get smaller, right? Okay, yeah, sure. And let's proceed, but that minus 1 could make a problem. Let's check. Okay, from this part the contribution was e power, okay, wait a minute. So we are considering just this times this, right? And the contribution from this part was e power t times real part of z, which cancels this out, and then so e power zt times 1 plus z squared by r squared times 1 by z. This one is uh, this one was exactly what? E power real part of t times real part of z divided by r squared, right? And r squared times real part of z, right? Two real part of z, right? Okay. Yes, right. So when we multiply this and this, we get 2 by r. Okay, whatever cancel. I mean, what cancels? Real part of z cancels. Below we have r squared, and then upstairs we have e power minus t minus. Oh, but we in the below we are having r squared, and that's fine because now this. I mean, at first we will take that r is going to infinity, right? So this will not make a problem then, right? E power minus t real part of z greater than 0, sure. So it is being greater than 1, right? Yes, so it is become positive. Yes, right. So that and we actually this is not going to make a problem because at the bottom we are getting an r square anyway. Right, right. Yes. Yes, we can write f of oh, yeah, of course we can indeed. Yeah. Thank you. So now that means the integral over this part c minus of this gtz times e zt 1 plus z squared by r squared, this dz by z, this remains bounded by, tell me what did you get? 2b by r squared, and as you just mentioned that this is since this thing is larger than 1, so this would be less than it is visible for everybody, maybe I put it up here and write that this is less than b by b times e power minus t real part of z by mod of real part of z. Okay. And so when you multiply it with whatever we are getting from gtz, we are just getting that it is less than equal to 2b by r again. No, wait a minute. Yeah, 2b by r again because we are taking the contour again on the c on c tilde, right? Okay. So now what happens? Now what terms are left? We have still to consider this integral, not c tilde, not over c tilde, but c over c minus with g here, g0. Sorry, I mean the original g here, right? We cannot shift the contour to C tilde for G, because all we know is that G is analytic on this line. Okay. So again on yellow part, integration of C, integration of over C minus of Gz times e power zt 1 plus z squared by r squared dz by z. Okay. So we're considering this one, and note that now over this, if you just think of the rest without thinking of this, I mean, suppose this is not there and you are integrating this on this on the yellow part. Okay, this is analytic, this is analytic. Okay, and wait a minute, yeah, 1 by z also doesn't make any problem because it is I from 0, right? Okay, so both are analytic. Actually, it's just, I mean, it's a continuous function on a compact set, right? So what do you know about that? It's bounded, right? So the integral of this, I mean, everything except, I mean, if you consider it without this one, this remains bounded, right? And note that zt, I mean, t is, sorry, z is negative here, right? I mean, the real part of z is minus delta. So if you take the absolute value there, you get, so this one is less than equal to integral of integral over c minus over some function which remains bounded, that is this one. So you can take that bound, I mean, call that bound some m, say. So this is less than equal to then m, and here this one, right? Okay, and this is just m integral over c minus e power minus, okay, e power real part of z times t, right, dz. Okay, but real part of z here is negative, right? um, yeah, so real part of z is, okay, wait a minute, we can actually write immediately that this one is c minus e power, and here let's write it clearly. Okay, so this is absolute value of minus delta plus some it times capital T dz, right? Now this it t, absolute value for that of that is just 1, right? So this becomes then m times integration of over c minus e power minus delta t, and this, now since the real part of this is negative, this one is, I mean, this one could be made as small as possible, right? dz, and this one is, I mean, this is just basically the real part of z, of course. Not minus real part of z, that is delta, that is minus delta actually. So I just wanted to expand this to absolute value of, yeah, right, yeah, okay, right, length of, because it's just a compact thing. I mean it's about, so it's about this length, right? So then this remains bounded by well, just this remains bounded by some constant m dash. Okay. Yeah. Mod z, mod dz, right? Yeah. Yeah. And that is a length you mean? Yeah. Right. Sure. Okay. And that means, well, not only that, this one actually converges to 0, right? Because you can take t going to infinity and the integrand is just 0, okay? And you are integrating it over a finite length of the contour from here to here, right? So the entire thing here goes to 0, okay? So all you have to now work with is this 2b by r, which is coming from the other two parts. Now if you take the radius of this contour, I mean this half radius, to go to infinity, that will make the other two part also to go to 0, okay? And that means you are getting indeed that the integral of this 1 by 2 pi I integral over C, the entire contour g0, sorry, gz minus gtz e power zt times 1 plus z squared by r squared dz, this is equal to, I mean, as r goes to 0 and t goes to, as r goes to infinity and t goes to infinity, this goes to 0, right? T goes to infinity and r goes to infinity as well, okay? Dz by z, thank you, yes. Yeah, that was the kernel. Thank you very much. Yeah. So now once we have shown this, that means what? That limit g0. So this was giving you g0 minus gt0, right? Now if you take this limit, well, r has nothing to do with the left hand side, but t has. So that means that this one goes to 0 as t goes to 0, right? So that would imply that, yes, indeed, t tends to infinity. Yeah. So limit t goes to infinity, gtz, that is gt0, that is giving you g0 indeed. Okay. So that settles the claim that we had, that xi x, I mean, if so, now in order to show that xi x is asymptotic to x, it remains to show what? We have got that this, I mean, that xi x is asymptotic to x, this is equivalent, not equivalent, this will be implied by the convergence of this integral xi x minus x by x squared over the range from 1 to infinity, right? And then we saw that if this function, if you replace that x squared in the denominator with 1 plus s, and if that is analytic over the real part of I mean in the region where real part of s is greater than or equal to 1, then we are done, right? So now the task becomes to show that it is analytic on that region. So we are trying to show that psi x is asymptotic to x, which is implied by the convergence of this integral psi x minus x by x square dx from 1 to infinity. This converges, and this would be implied by the fact that psi x minus x by x power 1 plus s is no, not this one, the integration of this from 1 to infinity dx is analytic for real part of s greater than equal to 1, right? And we will see that this connects to the non-vanishing of the zeta function on the real line s equal to, I mean real part of s equal to 1. Not on the real line, of course it has several trivial zeros on the left, so it's about the line real part of s equal to 1. We will just show this. At first we compute this, okay, this integral, and see what it is exactly. So now look at this 1 to infinity psi x minus x by x power 1 plus s dx. We'll see why it is an analytic function for real part of s greater than or equal to 1. Okay. Now psi x is sum over log p for pk less than or equal to x, right? Minus x by x power 1 plus s dx. Okay. And we still have to wait for 2 minutes when the electricity is back. Okay. All right, so this one now becomes what? We separate this out. Okay, so this one is just 1 to infinity summation log p power k greater than or equal to x, sorry, less than or equal to x by x power 1 plus s dx minus, I mean we are in the region real part of s is greater than or equal to 1, so there none of these integrals will have any problems of convergence if we separate this out. Okay. X to the power s 1 to infinity. Now can you tell me what is this? We did it yesterday also in afternoon, right? This is an easy integral. We explicitly did this, right? This was only this part, say. Yeah. So integral from 1 to infinity x power minus s, yes, 1 by s minus 1, and that's it, right? Because it is the other limit is infinity. Yeah, sure. Okay. And what happens with the other part? So there is the sum from 1 to infinity, sum over log p, pk less than or equal to x. Now at the bottom there is x power 1 plus s, right? So for each, wait a minute, so what are you integrating here? It's a sum over the von Mangold function for up to, I mean the series. Okay, wait a minute. So this is the integral from 1 to infinity summation lambda n less than or equal to x by x power 1 plus s dx, right? And we proceed with this in a moment after we take a 10 minutes break, because it has been more than 1 hour.